Okay, so let's look at an example how we're going to use this and how we're going to define the failure envelope. So um, this is my test setup. I'm choosing P equals 2,000 pounds, and we're going to increase F until failure, and the end result was that I get this curve here with an F max of 850 pounds. So this is F versus delta. There's my F. My delta is the deformation there. And the test setup has a cross-sectional area of 0.08 square feet, and my goal is to find phi prime. Okay, so the solution is, I'm looking at the test, I have set up this little spreadsheet. We have our P, A, sigma prime, FF, FFF, then tau FF. So this is in the sample is in sand, so I don't have to worry about any excess pore pressure or anything like that, because we're running it by definition at a slow speed, so no excess pore pressure is generated by the shear test. And so what do I see? Well, I know that P is 2,000 pounds, it's given. The A is given to be 0.08. P over A gives me the sigma prime FF. It's 25,000, so that's straightforward. So I get my sigma prime FF, and my FFF, well, F max is 850. There's my F at failure on my failure plane. And then I simply divide that by the cross-sectional area, 0.08, and I get my tau FF is 10,625. So what's of interest here? My sigma prime FF and my tau FF. I plot those on my tau sigma prime plot, and it's that point right there. I draw a line from the origin to that point, and what do I see? I can get this little triangle here, and I use that triangle to get that the tangent of phi prime is 10,625 over 25,000. I get that the tangent of phi prime is 0.425. That gives me that phi prime is 23 degrees. And that's my answer. My friction angle for this problem is phi prime equals 23 degrees. Let's look at an example in clay, and I need to run at least 2 tests in clay, and we're going to say that we're running these tests slowly. So this is I should write this down, that the test is slow. So that tells, okay, so that tells us it's a drained test, and our goal is to find C prime and phi prime. So I've run 2 tests. I run one test at P equals 100 pounds, and I get that curve. I run another test on the same soil, not the exact same soil, but the same soil type, different part of the sample or a different sample of the same material. I run the second test at 300 pounds, I get this. And here I have a peak of 30 pounds, here I pick a peak of 60 pounds, and my goal again is to get C prime and phi prime. In the solution, well, I'm running two tests, 1 and 2. My P's are 100, 300. The cross-sectional area is given to be 0.1. So I get, P over A is 1,000. P over A is 3,000. So I get my sigma prime FF. My FFF is given to be 30 and 60. And F over A is 300. F over A is 600. So I now have my sigma prime FFs and I have my tau FFs. I plot those 2 points on plotting sigma prime versus tau. I plot 2 of them. So I have my points 1,300. The other point is 3,600. I draw a straight line between those 2 points, and it's going to have an intercept. And now I just use basic trigonometry to get the slope and the intercept. That's what I want. So I get the slope is what? Delta y over delta x. You can all do that. I get a slope of 0.15. And that means that my phi prime is the arctangent of the slope is 8.53 degrees. Then I use y equals mx plus b, which since my y is my tau and my x is my sigma prime, that gives me that tau is equal to m, we just figured out as 0.15, sigma prime, and then the intercept is c prime. We've defined the intercept as c prime, and I use that. I can use either point. I can use that point or that point. I decided for this one I used this point, 1,300. So my y value is 300. My x value is 1,000. I solve for c prime, and I get that c prime is 150. So that defines my failure envelope. So this is my answer. Phi prime is 8.53. C prime is 150 PSF. So again, summary for drain strength. What do I have? I have sigma prime on my x-axis. I have tau on my y-axis. And for sand and gravel, it goes through the origin. For silt and clay, it does not go through the origin. We have a C prime. The angles, the friction angle is phi prime. So drain strength parameters, what we call the drain strength parameters are C prime and phi prime, and again, this is our same page, but this is for drain strength. Know this page. You need to know the failure envelope for sand and gravel, failure envelope for silt and clay. Again, what does it mean? That means if we have, here's my failure envelope for sand and gravel, no failure if my stresses are down there. I have failure if I have my stresses above there. No failure if my stresses are below. Failure if my stresses are above. Now, what does that mean? For instance, we have our, let's say I have sand here. Here's my t equals 0 minus situation. I don't have any structure there. At t equals 0 plus, what happens? I have my structure in place. And what do I know? Well, when I have my structure in place, then I have my pressure bulbs here. So I can determine the stresses at various points in situ. And what I'm concerned about is this potential shear plane here. And so I want to get what the stresses are. I can get my sigmas. And then I want to know what are my taus at failure. That's along this. And that will tell me what my strengths are. And I want to make sure that if I take moments about this point, the weight of my structure, etc. I want to be able to make sure that there is no failure taking place along this plane. In other words, I don't get a bearing capacity failure. This is one way to analyze it. It's not necessarily the way it's always done, but that's the way we're going to look at this. So what we're going to do is we're going to have for instance, a sigma prime before the structure is built. So in other words, I know there are sigma primes in here in my soil. I can figure out what the sigma prime is before the structure is built, which gives me a tau ff before the structure is built. Now what happens after the structure is built? Well, what do I know? The sigma prime has gone up, and that means that my tau ff has gone up. So in a sense, what we find is that building the structure does actually two things. We get a bigger tau ff after the structure is built. So in other words, the structure does two things for us, in a sense. It actually increases our strength. The tau ff increases due to the building of the structure. At the same time, the shear stresses also increase due to the building of the structure. So we do two things. One, we increase the strength of our soil, so that's a good thing. But we also increase the shear stresses. So again, this is something we don't generally see in steel. It adds a little complication to this analysis. We have to take into account the changing of the soil strength along with the changing of the shear stresses. How else does this, what other analyses do we do? For instance, if I'm interested in evaluating the potential landslide, how can we evaluate it? Well, let's say we have this hillside looks like that. What can happen is that a portion of the hillside can slip off. It could be a wedge. If it's a wedge, then what do? I analyze this potential shear plane right here. I have the weight of the wedge, and then I have, if I need to interpret, what are my shear strengths along that failure plane, potential failure plane. Another potential failure plane is circular. Here, we take moments about this point. I have the weight of this mass. I take moments about this point, and I have to figure out my soil shear strengths. That's another type of analysis that we have to do for a potential landslide. Okay, as an example, what we're going to do is we're going to determine the drain soil strength, tau ff, in situ for these two cases shown. So we have, it's drained, so we're assuming drained loading. In this one, in the one on the left, we have sand, and the one on the right, we have clay. So the structure is the same. B equals 50 feet, weight is 8 million pounds. B equals 50 feet, weight is 8 million pounds. And we're just going to determine the soil strength, tau ff, at this particular point of interest. Now we've done the soil tests. I've determined that the friction angle in the sand is 33 degrees. For the clay, I found C prime and phi prime. C prime is 400 psf. Phi prime is 22 degrees. And again, at the point of interest, I want to find the soil shear strength at tau ff. So the solution is, the first thing we want to do is find sigma v prime at the point of interest. And I've given you the point of interest, and we have ZF over B is 1 for both cases. So I have case 1, case 2. What is going to be my what is going to, so I start out with my sigma v. Okay, so I'll start there. Notice that the point of interest is a depth b below, so the depth is 50 feet. So the depth of the point of interest is 50 feet. So when I'm looking at the stresses at that point of interest, I'm going to have, I have my gamma, the soil's saturated below the water table. Both soils have a unit weight of 120 pounds per cubic foot. So to get my soil stress sigma V, what is it? It's going to be 50 times 120 for both of us. That's for both of them, because it is 50 feet of soil. But what else do I have to include? I've got to include the stress due to the weight of the structure, and the weight of the structure is 8 million pounds. The area is 50 squared. And then if I look at my pressure bulb, it's times the pressure bulb factor is 0.25. I'll let you, it's below the edge. Notice it's below the edge. So I get 0.25. So I get my sigma V at those locations is 6,800. I get my U water table. Notice slow loading is drained. There's no U excess. Okay, so no U excess because it's slow loading. So I get my U water table is that. That gives me my sigma V prime. But then how do I get my tau FF? Well, my tau FF, I have to use the failure envelope. So for sand, it looks like this. I have the 3680 from the sigma V prime, and I know that this is given as 33 degrees because that was given information. And I get my tau FF from the 3680. That's that. And I just use geometry. Tau FF is 3680, tangent 33 degrees. I get my tau FF is 2390. For the clay, what is it? I have to use both the C prime, which is the intercept, the phi prime is the angle, and now the geometry is just slightly more complicated, but I also have my sigma prime of 3680. I now need to get this. Well, I break it into two parts. So this is 400, and then I create this little triangle here, and that is going to be 3680 tangent of 22. So I simply add the 400 to the 3680 tangent 22 degrees. So I get the 1487 plus the 400. I get 1887. So I've got the tau FF at that point for both these situations. For the sand, it's 2390. For the clay, it's 1887. I could use that in. Okay, so now I have a different point of interest, and I'm now going to take this point of interest here. Same situation, but now my point of interest is 20 feet. It's close to the other edge over here. So I want to know what is the soil shear strength there. Well, if you look here, in both cases, the failure surface is approximately vertical. Okay, so now I have a vertical failure surface, and down here the failure surface is horizontal. Failure surface is horizontal. Over here the failure surface is vertical, so how does that affect my tau FF? Well, I have to use the K naught in this case. I'm giving you the value of K naught because now since the failure surface is vertical, I need to figure out what is the normal stress to that vertical. Well, the normal stress is a horizontal stress, so I need to figure out the horizontal stress, which means I need to use the K0 to do it. So what we're going to do is we're going to find the sigma v prime at the point of interest, but then we're also going to need to find the sigma h prime. And we've done this with our wall calculations. In this particular case, what we see is ZF over B is 20 over 50. And so that's going to figure into our pressure bulb factor. So this is similar to the previous problem, so I'm not going to go, I got the 20 times, now it's 20 feet down, so I got the 20 times 120. I have the weight of the structure divided by the area of the structure. And now my pressure bulb factor in this case is 0.5, and I get a sigma V of 4,000 now. My U water table, as we all know, 20 times 62.4. So I get a sigma V prime. I can get a sigma H prime by using the K0s. The K0s. So I get those sigma H primes. Now I'm going to use the sigma H prime in my diagram. So 1156, I use 1156 and get my tau FF. 1734 and get my tau FF. The geometry is the same, so I'm not going to go through it. So I get that, 1156 tangent 33 degrees for this one. I get 751 for my tau FF there. For this one, I've got 1734, and then I have the 400 plus the 1734 tangent 22 degrees, 701. So I add the 400 plus the 701, and I get 1101. So I'm able to get the tau FF at different locations along this circle. Okay, so I want you to work this problem. So you can pause the video. Determine the drain soil strength, tau FF in situ. This is dry gravel, so you don't have to worry about U water table or anything like that. And I want to get at this point of interest right there. And I want you to assume that this failure plane is approximately vertical. And I've given you the K0, so it's going to be similar to the other one. And so the shear surface is approximately vertical at the point of interest. And what I want you to do is fill out this table. And it's, as I say, it's dry gravel. You need to take that into account. You need to draw the failure envelope, the proper failure envelope down here. I've given you some information right there that you can use to draw the failure envelope. And then your goal is to get the tau FF at the point of interest. So pause the video here, fill out this table, and do this problem. Okay, I'm going to assume that you've done the problem. And so what do I have? In this particular case, there's no building, so it makes it much easier. Depth is 18 feet. It's dry gravel. 18 times 103 gives me 1854. There's no water table. Sigma V prime is the same as the sigma V. Now, how do I get my sigma H prime? I simply multiply times 0.45. And I draw the failure envelope. The failure envelope, it's given, well, C prime is 0. It is because it's gravel. I got 31 degrees. I put the 834 here. 834 tangent 31 is 501. I get 501 for at that particular point of interest. Now, of course, to do a full analysis, we do other points around here, and then we get various shear strengths. Okay. All right. I'll stop there.